Well, welcome back, everybody, as we jump into some more polar stuff. And in fact, today's kind of a benchmark day in the sense that up to this point, all of our polar work has been with regards to the pre-calculus topics. Today's the first day we're going to graduate and actually do some calculus in particular to these polar equations. And we're going to try to find the slope of a tangent line today and eventually write the equation of those tangent lines. However, I've got to be real honest with you here up front that I remember when I was in your shoes and learning this topic for the first time, my expectations were that probably nothing could be easier than finding, because how many times have we done slope already? How many times have we already written the equation of a tangent line? And, as we get ready to try to visualize, and here's a good example in front of us, so we've got a polar curve and a tangent line drawn at a specific point. As we get ready to find that slope, let me give you an example. What if we had the equation r equals 2 plus 2 cosine of theta or something like that? My instincts were that the derivative of r with respect to theta is simply going to be negative 2 sine of theta, and that if I wanted the slope at any given point, I could fire it into this equation to find slope. But, and this is the mistake that 99% of the students on the AP exam make. Here's what we need to know. This equation, okay, dr d theta, does not describe slope. All right? And that left me scratching my head for a while. What do you mean it doesn't describe slope? All derivatives describe slope. Not quite so fast. And I want you to analyze this sucker here. Okay? It's the change in r over the change in theta. Okay, the change in r does not describe or measure rise, all right? And d theta does not, okay, and I should probably put the word not there, all right, does not describe the run, all right? So a polar derivative with respect to his independent variable doesn't do us any good when it comes to slope. So what do we know about slope, all right? We're going to go back to, virtually, I don't know what grade it is. Was it fourth grade when you first do slope? Okay, slope is defined as rise over run. All right, just like when you look at the side of a house and you look at that roof and you're measuring the pitch of that roof. Here's your run, right, and there's your rise. All right, and that the ratio of those two components will tell you the slope. So then we said, well, rise is really the change in the y value, and run's really the change in x, and that described the average rate of change over a certain interval. And then in calculus, we graduated and we said, well, we're going to make that change in y and change in x infinitely small, so we've got dy over dx, and there's your slope. All right, so somehow we have to get this dr d theta over to dy dx. Well, here's the good news. If I took the derivative of y with respect to theta, and then I divided that by the derivative of x with respect to theta, do you agree, whoops, that should be a theta down there. Do you agree that this complex fraction right here is equivalent to this simpler fraction? Okay, and it's just a matter of, instead of dividing by a fraction, just multiply by his reciprocal, and you'll see that the d thetas cancel out, and this truly is just dy over dx. So what we know, and you'll notice here we're deriving the formula today rather than me handing it to you on a silver platter. All right. For instance, you guys learned in pre-calc that y is equal to r times the sine of theta, emphasis on times. If you want the derivative of y with respect to theta, we're going to use the product rule right here. All right. So the derivative of y with respect to theta is the first times the derivative of the second plus the second times the derivative of the first, which in this case is dr d theta now. And it's make sure that we know that all those derivatives are with respect to theta. So I'll tell you, the bad news is there's no cleaning up there. All right, that's the bad news. All right, now we also remember from pre-calc that x is r cosine of theta. That's one of our big four rules also. I'm going to take his derivative with respect to theta, again using product rule. So we've got the first times the derivative of the second, got your negative sign in there, plus the second times the derivative of the first. And I know a lot of you guys probably do your product rule backwards from me, and that's obviously legit. We've been doing that all year, and it is commutative. So those are my two main components. And we're going to move on to the next slide. We're going to put it all together. We're going to show you what dy dx looks like in polar. So we said that slope is, no matter what language you're speaking, slope is always guaranteed to be rise over run, all right, which is dy over dx, which we extended and we said, okay, we could say dy over d theta divided by dx over d theta. All right, so now I'm going to recall what I had on that last slide. dy d theta is really r cosine of theta plus sine of theta times the derivative of r with respect to theta. In the denominator, I'm going to slide the negative here, is r sine of theta plus cosine of theta dr d theta. So ladies and gentlemen, the bad news is anyway that this is your formula right here to find the instantaneous slope of a polar graph at any specific point. It's rather long, obnoxious. I think it can be difficult to memorize, and that's why I don't necessarily memorize it. I just know from pre-calculus that x is r sine of, or r cosine of theta, and then I do my product rule. So that's how I kind of build this formula. When I see it on a test, I don't necessarily memorize it, but maybe some of you guys will pick it up really quick and memorize it, and I encourage you to do so if you can. So now we're going to jump into a couple of examples and see how this bear works. Alright, so here's our first example. First of all, the directions are asking me to sketch the polar curve and then also sketch that specific tangent line. And then we're going to find the instantaneous slope at the given value of theta. And also, just for beginners, I just took the liberty of rewriting that slope formula in front of us. And anyway, so here's what the problem might say. They might say, let's consider the equation r equals 2 cosine of theta. And they may want the slope of the tangent line at theta equals pi over 6. Alright, so that's what I want you to consider. And so as far as sketching this goes, I still, habits are habits, I guess. And I still do a real quick rectangular sketch. Here's what 2 cosine looks like, alright, with an amplitude of 2. We should say height of 2, depth of negative 2. Now as far as what that looks like on a polar graph, and again, we probably don't have any more polar paper in front of you, and that's fine. I do most of my polar sketches on just a blank piece of paper. Let's see, I know I'm going to start out here at 2, and then we're back to the pole, and then at pi we're negative 2, which duplicates this point, and so hopefully you were expecting a circle before we even started. I'm going to see if I can erase some of that. Let's see if we can redo some of this a little bit here real quick. Okay, that looks slightly better. So you were expecting a circle symmetric with respect to the old x-axis. And we knew that we were going to be able to draw that circle within the first pi radians. Anything beyond pi would be just retracing the same circle we already have. So now we want to try to visualize where pi over 6 is. And I think this is one of the more exciting parts. Try to picture what we call a radial line at pi over 6. So I'm going to say, okay, that looks like 30 degrees roughly, and that's where that line takes me if I follow that line straight to the curve. And then we're going to try to draw a line tangent to the curve right there. Here's where it could get real interesting. Not too bad. Not my worst line. But anyway, so you're visualizing definitely a line that has negative slope, and that's one of the reasons I like doing the sketch, is because if we do all this work and we end up getting a positive answer, we know that we got to tap the brakes, go back and figure out what we did wrong. Alright, now it's time to really get down to the nitty gritty. So let's say that our slope, dy dx, is really, and I'm just visualizing this formula at the top, and when you see that r, I'm going to substitute 2 cosine of theta in for that r. And then the cosine of theta is already built in, plus the sine of theta. And then when you see dr d theta, I want you to substitute negative 2 sine of theta, because that's the derivative of this equation that was given to us. On the bottom, we've got 2 cosine of theta, and then we've got the sine of theta already built into that formula, plus the cosine of theta, and then negative 2 sine of theta. Now I mentioned earlier that I think it's kind of challenging to memorize this, but here's what you do know. Based on the way that we set ours up and we wrote ours at, we know that this quantity is the same as this quantity. So these two line up with each other. And then after that, these cosines flip-flop, the sines flip-flop, and then these quantities are the same. So it's like same, flip-flop, and then same right here. And that's just kind of a point of reference to maybe help you check your work after you get it all set up, see if we're right. Now from this point on, I used to do a lot of multiplying and distributing and combining like terms, and you'll notice there is a lot of cleaning up you can do to this derivative. And especially if you're comfortable with your double angle formulas, you can go really hog wild and clean these rascals up. However, over the years, I've kind of changed my tune a little bit, and I said, you know what? I'm going to resist all of that cleaning up, and I'm just going to substitute my angle in there right now. Okay, I'm just going to plug it in right now and start chugging. So we've got 2 times, let's see, radical 3 over 2. And then I've got another radical 3 over 2. I've got a 1/2. And then I've got negative 2 times 1/2 here. Let's see, got my negative. 2 times radical 3 over 2. I've got my 1/2. Got my radical 3 over 2. And then negative 2 times a half again. All right. So at this point, some of these problems are going to clean up nicer than others. But go ahead, try it. See what cancels. See what you can combine, and see how clean you can get this. All right. So here's what I was thinking. I thought that, for instance, these 2's canceled. And then when I multiplied these rascals, I had just 3/2. And then I came over here and I said these bears cancel, so I just ended up with minus 1/2. On the denominator, again, I said these bears cancel. I ended up with negative radical 3 over 2. And what do we got over here? I think we got another negative radical 3 over 2. So again, just trying to clean this up. Let's see, I think we got a 1/2 in the numerator. Negative 2 radical 3 over 2, bang, bang. Let's see, that's over 1. So I've got 1/2 times negative 1 over radical 3. We don't have to rationalize this, so let's just say it's negative 1 over 2 radical 3. And let's say that's the slope of my line. Good news is we got a negative answer, and we knew visually from our sketch that we had a negative tangent line right here. So that, at least that part kind of agrees with our common sense. So there's our first example. I think it's a lot more work than you were expecting to do for, a basic question like find the slope. But the AP does recognize that it's a lot of work, and they're going to reward you point-wise for all this work. All right, we're going to jump in. We're going to try to extend this concept a little bit. We're going to ask you to write the equation of the line tangent to the polar curve at a given point. And so I've presented you with one of my favorite polar curves, a nice inner limicon with an inner loop, r equals 1 plus 2 sine of theta. And we're going to try to write the tangent line at the moment when theta equals pi. Now, just for a real quick sketch here, again, and we can do the rectangular one first and then the polar one. Here's the rectangular, we're going up 1. We've got an amplitude of 2, so we get just below there. So here's what my rectangular curve looks like. And then now more specifically, here's what that dynamic polar curve. Let's see, we're going to hit 1, and then we're going to hit 3, and then we're going to hit 1, and then we're going to hit the pole, and then at 3 pi over 2 we hit negative 1, and then we're going to hit the pole again, and then finish back where we started. So we've got a curve that generally looks like this. Okay, one of my better ones, not too shabby. It's really tough to approximate the slope just by looking at the sketch, of course, because it's like our curvature can fluctuate so much and whatnot. But anyway, here's where pi is. And so I'm trying to visualize a tangent line at that moment. So I'm visualizing this line right here. This is the line that I want to write the equation of. Now, as we describe that line and write the equation of that line, even though it's tangent to a polar curve, they're going to expect me to write the equation in rectangular form. All right, so the good news is here, and this is actually good news, trust me, we're still going back to this form, y minus y1 equals m quantity x minus x1. All right, so we're still going to write that. Now, what we got here is not only do we have to use that long obnoxious formula to find the slope here, but we also have to find that point's corresponding y value and x value in terms of its rectangular coordinates. But what we're going to find out is it's really not that much extra work. So actually, I'm going to go ahead and get the x and y coordinate out of the way right away. We know from our big 4 that x is equal to r cosine of theta, which means in this particular example, we're going to substitute that equation 1 plus 2 sine of theta in for the r. And then what I'm going to do and you notice, I think I used this notation on the last problem, and I maybe didn't make a comment on it, is when you want to specifically evaluate that equation at a specific value of theta, I just use that kind of notation. I draw the long vertical line, and then I put a little subscript, theta equals pi, to show that I'm going to evaluate it at pi. So let's see, sine of pi is 0, so it's 1 plus 0 is 1, and then the cosine of pi is -1. So we've got an x-coordinate of -1, which I don't think just would surprise you by looking at that picture. And then we're going to say that the y value is really r sine of theta. And for this particular example, we can substitute 1 plus 2 sine of theta in for r. And if we evaluate this rascal at pi, so we'll use this notation here, theta equals pi. Let's see, we're getting a 1 times a 0, which is a 0. Again, I don't think that's going to surprise you by looking at the picture. The reason I just wanted to, even though we could have done it visually, I wanted to go over the process because it always won't be that easy. So start what you know from pre-calc with the big 4, substitute into there, and then evaluate. Now, the only thing missing now is my slope. Alright, so here's where the real bread and butter comes into play here. I'm going to take my time and I'm just going to rewrite my slope formula, and I'm going to encourage you to do that right now. Go ahead, I want you to hit that pause button and see if you can write down, see how much you can write down without looking. Alright, here's what I came up with. Just a few pointers here again. Remember, these two are the same, and then you're going to flip-flop those rascals, and then these bears are the same. So that might help you remember it. And then don't forget that pesky little negative sign down there. That's one of the more common mistakes, of course. Now, as far as we go for this particular example, I'm going to go ahead and I'm just going to substitute appropriately. I got 1 plus 2 sine of theta going in for r. Let's see, we've got our sine of theta here. We've got 2 cosine of theta for our derivative, negative 1 plus 2 sine of theta. We've got our sine plus our cosine, just a lot of writing, and then our derivative 2 cosine of theta. Okay, now we are ready. We mentioned earlier that there's a lot of cleanup we could do, but we're going to avoid that, and we're just going to evaluate this derivative at pi to get our slope. Okay, let's see. I love the fact sine of pi is 0, so that gives us a 1. Cosine's -1 plus 0 times something, which it doesn't matter. Let's see. I get a 1 times a 0. Let's see. We get a -1 times a -2. Okay, clean it all up. I think we've got -1 over -2, which is 1/2. So we've got a slope of 1/2. Ladies and gentlemen, we are coming down the home stretch. We are ready to put it all together. I'm going to say y minus 0 equals 1/2, and then x plus 1. So we found everything we needed. We got our x-coordinate was -1, our y-coordinate was 0, our slope was 1/2, and ladies and gentlemen, we've got the equation of that tangent line in rectangular form. And again, I just wanted to leave you with one last statement here, is just to use that correct formula. So many times we try to oversimplify the concept of slope of a polar, and just keep telling yourself that the derivative of r over the derivative of theta does not describe rise over run. Okay, this does not equal slope in even the slightest regard. It's not even close. It's not even close. We have to do dy over dx, which involves more work, but obviously it's going to get us the right answer. Good luck on the sheet tonight. I'm looking for good sketches, correct number crunching. I don't think you need the calculator for anything, but I'll also post my work on the website there somewhere where you can find it, probably right on the calculus homepage, so you can compare your answers, and just make sure we get them submitted on time. See you guys.